morning, everyone. This is Dr. B. Polaiah, working as a professor in Department of IT at the Institute of Aeronautical Engineering, Hyderabad. I'm very happy to share today my knowledge on one of the topic as named as detection of discontinuous in image processing. So the topic detection of discontinuous in image processing is a topic which we are covering under the syllabus of image processing. So this process I am starting now from now, as we can have in the continuation of knowledge. Okay, so the topic which I am covering here, detection of discontinuous in image processing, how we are actually concentrating this in the sense we have already the knowledge about image segmentation. Such image segmentation divides an image into regions that connected and have some similarity within the region and some difference between adjacent regions. That is, the goal is usually to find individual object in an image. For the most part, there are fundamentally two kinds of approaches to segmentation. That is, the fundamental two kinds of approaches are discontinuities and similarities under the segmentation. So the similarity may be due to pixel intensity or color or texture. So differences are sudden changes, nothing but differences are sudden discontinuous in any of these, but especially sudden changes in intensity along a boundary line which is called an edge. So this edge we are finding in the same of sudden changes in intensity along with the boundary line. So coming to the there are the three kinds of discontinuities which we are representing in the name of one mathematical analysis, that is R equal to W1 Z1 plus W2 Z2 so on W9 Z9. So this equation usually actually concentrating on finding of that discontinuous of intensity in terms of points, lines and edges. So how we can distinguish that points, lines and edges? Let you consider one general task image, which is a general 3 by 3 mask image, which represent 3 by 3 mask image. So this image usually we used to represent in terms of most common way to look for discontinuous is to scan a small mask over the image. The mask determines which kind of discontinuities to look for. So here, such a discontinuous we may find to keep one of the region that we take the matrices which we are simply says about 3 by 3 matrices, 3 by 3 matrices, which is point A. Let us assume this one A figure is B and this is C. Okay, what is the A says? A says is a point detection of the mass. What is B says? Say X-ray image of a turbine blade with a priority. What C says? It's a result of point detection. What is will be you want to concentrate much more result which we are in the continuation for understanding such a resultant of information will compare with the originality. We going to have X value that we are going to be treated to in terms of matrices by comparing with a certain threshold. The T is nothing but non-negative threshold value. So coming to the in the similar example, which we are in the continuation of the same, let you going to have such a edge detection which we are applying here, the model of an ideal digital edge, model of a ramp digital edge. This is we are applying in terms of standard step function. Okay, standard step function, and we call this one is a also standard ramp function, ramp function signal, functional signal. So what do you want to understand in between these two? By applying this to the gray level image profile, horizontal line through the image, you may going to find out the part of information which we are wanted to see the ideal edge and the ramp edge. You see here, this part alone, we may find the linearity. Here we find this part and this part alone. So like that, you are going to see the model of an image, ideally digital edge, and model of a ramp edge, the slope of the ramp is proportional to the degree of blurring in the edges. So that we are going to be find through the this signal. So the detection of discontinuity in by edge detection, which we are going to be apply here. Let you take the image. This is the your figure. This is your figure. So what this figure says? What this figure says? This figure says this is the figure. Okay. What is this figure says? This the figure shows two regions separated by a vertical line. Separated by a vertical line detailed near the edge, showing a gray level profile and the first and second derivatives of the profile. So by the help of this, we can find out the your discontinuities. What the ramp? This is the ramp signal. What this ramp says? It detects at the edges of the any error. It detects at the edge. So we differentiate in order to first order differentiation. We'll get the pulse. We'll get the pulse. That is, you'll get the signal. Second order differentiation means we'll get the reverse step value. You will get the reverse inverse of the step. So what we want to understand from here, you are going to take the image, which in terms of this is the image. Let us take this is image. This image you are taking and proceed to find out the your what we call discontinuities. The first column images and gray level profiles of a ramp edge corrupted by random Gaussian noise of mean value 0 and the sigma which we are representing here in terms of noise of image and sigma values respectively. So if you go to the second column where this is first column, where we go to second column, if you go to the what we observe here is first derivative of the image and gray levels profiles will be find out from here, and we find out the noise also. We find out the noise also. We find out in the sense detection. So the third column, which is here, we find out according to the second differentiation equation of the image, and the gray level profiles also will find out. So similarly, what we want to understand from here, the example which we are in continuation towards to understand the values which we are changes here respectively. Based on this value changes, your profiles will be changes. Your profile level of that is gray level of levels will be changes. So that means coming to the point, so far we generalize the equation and we concentrated on detection of discontinuities in image processing, but where we apply the certain operation name we call a gradient operations, the first order derivative which help us to find out the your gradient operation. So gradient f is equal to gx gy, where gx is with respect to partial differential equation and gy is also with respect to dou f by dou y. What do you mean this? That is, if you take one standard image which is in the form of f of x comma y as an objective that we named as the gradient of an image object f of x comma y at the location of x comma y is defined as the vector in terms of gradient operation is this equation. Okay, this equation. So this equation now we can modify into magnitude level and direction, because it is being a vector, though you know the definition of vector, that is in terms of magnitude and direction. Okay, so what is the magnitude of your vector is dou f is equal to magnitude of dou f is equal to g square of x plus the gy of x square all to the power of 1 by 2. So, and the direction of the vector is, that is alpha of x comma y tangent, that is tan inverse of gx by gy. What is this? These two are the standard formulas where we are concentrating on the gradient operations. So, coming to the gradient operations, that is robots across gradient operations, which we are applying to the standard image, and we find out the values in terms of changes robots, so that we find out here the differences also changes, rows as column rows, but sign value changes. Grid operator is right now here it is 2 by 2, here it is 4 by 4, here it is also 4 by 4, but point is, sorry, here it is 3 by 3, 3 by 3, that is 2 by 2, this is 3 by 3, 3 rows, 3 columns. Okay, so that Sobel operators here. So these are the standard operations. Even we can extend that private mask for detecting the diagonal edges. We're going to get your values in the similar. Sobel mask for detecting the diagonal edges. You can see the, by comparing these two figures, we may understand detecting the diagonal edges. So, detection of discontinuous gradient operations, the best example is here. Let you take the original image. This is your original image, and you pass to the your component of the gradient in the x direction. When we pass the x direction, a component in the y direction, then we are going to have the your b part. That is your figure b, and you are going to see concentrating on vertical. This is horizontal. That is x. Here vertical, that is y. So then we will find out the figure C. What is this component in the y direction? How it is look like this image. And the component like a D. D means gradient image. What is the formula of this gradient image? Is you have dou f is equal to, that is approximately equal to g of x plus gy. So then we'll get this. So you are going to have that detection of noise, in the sense detection of discontinuous, by applying gradient operations as best example by comparing these figures. So in case of as we concentrate that gradient operators with the help of first order derivatives, where we going to have second order derivatives also, which we are applying in terms of Laplacian formula, that is the Laplacian of 2D function f of x comma y is defined as dou square f f by dou x square plus so this partially it is second order. This is second order equation. What do you mean second order? So that is you're concentrating on derivatives. Okay, two forms in the partials. Laplacian mask used to implement that equation. Okay, this equation as here will be going to be concentrated and applied, and your standard image values, how it may be changes in terms of second order differentiatives, which we call as the Laplacian. So coming to the, when we concentrate in the consideration of the function as a Gaussian function, we are introducing here that is h of r is equal to minus e to the power of minus r square by 2 sigma square, where r is the your Cartesian coordination of the values, sigma is your the standard deviation here, the standard deviation. So the Laplacian of h is dou square h of r is equal to, that means you are keeping your h in the Laplace equation, but in terms of gradient operation we'll get this. So the Laplacian of Gaussian sometimes is called Mexican head function. It is also called the computed by smoothing the image with the Gaussian smoothing mask, followed by the application of Laplacian mask. So here, when we concentrating the Laplacian of a Gaussian, that is we call LOG, in terms of 3D, 3D plot. So it can look like this one. Okay, and the cross section showing zero cross section here. This is zero cross section, zero cross section, zero cross section values. So with this, what I want to refer some more books which help us for understanding some more detailed information about the detection of discontinuities in image processing, which we can refer by using the list of reference. Of course, you are all enjoyed by listening this discontinuous detection of discontinuities in image processing is one of the important topic which we can concentrate for real-time applications also. With this, I want to close and the remaining topics which we are going to be continuing in the coming classes. Thank you so much for your patience. Thank you. Thank you so much.
Like, share and subscribe. Hit the bell icon for more updates.